Okay, so we want to continue with Themo 2, and for this particular lecture, we've covered quite a bit of it from the videos we've made on the Apsis YouTube channel. So you can just go through it. We're able to cover um, everything from the first part or from the start up to the end of, or just before we started with gases, mixtures of gases. So we spoke about the Gibbs-Duhem equation, we derived it, then we solved examples, right? So today we'll be starting from the ideal gas mixtures. What I recommend is that if you've not already gone through the previous videos, you do so before you start with these ones so that you don't get confused. Okay, I mean, they are not too many similarities. What we are come to talk about is entirely different, but I feel like in order to really follow the order, follow the structure so that you don't end up mixing things up, it's best to go through the previous videos before you start with these ones. Okay, so when we talk about ideal gas mixtures, we are saying that the interaction between gases differs significantly from that of liquids because of the spaces between the molecules of the gas, and because the gas molecules have um, more space between them as compared to the liquid molecules, their level of interaction is not as much as that of the liquid. So if you look down here, we can see the gas molecules are more spaced or are further apart as compared to the liquid molecules. So the amount of interaction the molecules here would have with each other would be less than what the liquid molecules are going to have. So when we are looking at a mixture of ideal gases, we are saying that they have no excess molar property for volume because the interactions are not significant. And remember we said that the excess molar property comes about due to the interaction between molecules. So if there is no significant interaction between molecules, then we can assume that there is no excess molar property for our gas. So what this tells us is that the partial molar property for enthalpy will be the same as the molar property for enthalpy, and the same thing goes with internal energy, and then for volume as well. That's for ideal gases. So if you want to look at the entropy for an ideal gas mixture, this is the relation we can use. So we have y1, which is the mole fraction of the first component of the gas. So this, if you have two gases, ideal gases being mixed together, so y1 will be the mole fraction of gas 1, s1 will be the entropy of that gas. We know our Ru, our universal gas constant, right? Then y2 becomes the mole fraction of gas 2, s2 becomes the entropy of gas 2. And we can do the same thing for the Gibbs energy for an ideal gas mixture, right? So we know the y1, the g1 is going to be the Gibbs energy for gas 1, g2 is going to be the Gibbs energy for gas 2. When we talk about the composition of gases, we know how to find mole fraction and mass fraction. So yi, we are using it to represent the mole fraction of our components I in the mixture, and yi is given by this expression. So it's a number of moles of our species over the sum of all the moles in our mixture. So if I have a mixture of two compounds, compound A has 2 moles, compound B has 3 moles, it will be the mole fraction of A will be 2 over the 2 plus 3. So I don't think we should dwell too much on this part because we've gone through a lot of courses to know how to find mole fraction and mass fraction. So we are representing our mass fraction with W. That's the mass of our species over the total mass of our mixture, right? So we know the notations, we know the symbols. I don't think we should spend too much time on this. And the other thing is that, remember, if there's a dot on top, then it becomes a flow rate, right? So n is the number of moles, n with the dot on top is the molar flow rate of our components, right? M is the mass of the component, W is the mass fraction, yi is the mole fraction. If the m had a dot on top, it would have been a mass flow rate of our component. Okay, then we can find the molecular weight of the mixture. So this is equal to the mole fraction of each species multiplied by its molecular weight, and then we sum everything together. Or if you're working in terms of mass fractions, it will be 1 over the mass fraction of each species divided by its molecular weight. Then we sum everything together. So MWI is the molecular weight of component I, Yes, and MWM is the molecular weight of the mixture. So if you want to find the R of the mixture, it's going to be a RU divided by the molecular weight of the mixture. Okay. So you're saying that when you want to predict PVT behavior of gas mixtures, it's usually based on two models. So this is the part you are really going to spend more time on and focus on. Dalton's law of additive pressures, that's saying that the pressure of a gas mixture is equal to the sum of pressures each gas would exert if it existed alone at the mixture temperature and volume. So all we are saying is that if I have two gases, right, gas A and gas B, at the same temperature and volume, right, they will have a certain pressure. So the pressure of the system is the sum of these two pressures. That's what Dalton's law of additive pressure says. But for Amagat's law of additive volumes, it's rather adding volume. So we say that if I'm having the same pressure and temperature for two gases, I can find their volumes and add them to get the total volume of the mixture. So that's Amagat's law of additive volume. Now, Dalton and Amagat's laws, they hold very, very well when we have ideal gas mixtures, but they are only going to give us approximate values when we are dealing with real gas mixtures. So for ideal gases, these two laws are identical, they give identical results. Sorry. So Dalton's law of additive pressures and Amagat's law of additive volumes. You can also use them for real gases. They will give us some level of accuracy. Now we usually use them with a compressibility factor. So we know that normally PV is equal to ZNRT, right? When I'm using the pressure of the mixture, the volume of the mixture, the Z of the mixture, the T of the mixture. And to find our Zm, we can find this by finding the average Z. So maybe we find the Z for one species, the Z for another species, and then we multiply them by their mole fractions. So maybe I have oxygen, nitrogen, carbon dioxide in my system. I'll find the compressibility factor as though it was just oxygen. Then I'll do the same thing for the case as though it was just nitrogen, and then as though it was just carbon dioxide. When I finish, I multiply all of them by their mole fractions and add them together. So that's what we are just trying to see. The Z for the mixture. Sorry, so Zi is determined from either Tm and Vm. So if you are using the temperature of the mixture and the volume of the mixture, then it's Dalton's law. Now if you're using the temperature of the mixture and the pressure of the mixture, then it's Amagat's law. Because Amagat was looking at working with pressure and temperature, right? And Dalton was looking at working with volume and temperature to find our parameters. So if you're working with temperature and volume, then it's going to be Dalton's law of additive pressures that we are going to be basing it on. So at a particular temperature and volume, so you're going to work with the temperature of the mixture and the volume of the mixture. Now, if it's Amagat's law of additive volumes, remember for him, we were looking at a certain pressure and temperature. So we are working with pressure and temperature of the mixture. Okay, so another approach for predicting the PVT behavior of a gas mixture is to treat the gas mixture as a pseudo pure substance. So one of such techniques is what we call the case rule, and this technique uses a pseudo critical pressure and a pseudo critical temperature for the mixture. So what it means is that instead of finding an average Z like what we are doing here, what we're rather going to do is that we are going to find an average critical pressure and critical temperature. So it becomes a pseudo critical pressure and a pseudo critical temperature, right? So if we're working with Dalton's law, Amagat's law, we would have used our critical temperature and pressure and critical volume as they are, found our reduced temperature, reduced pressure, reduced volume, gone to the compressibility chart, read our Z, and then find the average Z. So we'll see examples of that very soon. But for case rule, what we are doing is that we are rather going to find an average for the critical pressure and temperature and then use them rather to find the Z's we are looking for. Right, so we'll see examples of that very, very soon. Okay, sorry about that. So we are seeing another approach is to apply a real gas equation such as the Van der Waals equation, the Penrobinson equation, etc. So for these equations, the Van der Waals, the Penrobinson, we know that there's going to be an A term and a B term. So for the A for the mixture, we can represent it with this equation, the B for the mixture with this equation. So B, we just multiply the mole fraction of the species with the B of the particular species, and then we add all together. For the A, we find the mole fraction of the species, multiply by A of the species to the power 0.5. We add everything together and then we square the final answer. Okay, so now let's take some examples so that it becomes more understandable to us. A rigid tank contains 2 kilomoles of nitrogen and 6 kilomoles of carbon dioxide gases at 300 Kelvin and 15 megapascal. Estimate the volume of the tank on the basis of the ideal gas equation of state, K's rule, compressibility factors and Amagat's law, and then compressibility factors and Dalton's law. So the first thing is we are going to estimate the volume based on the ideal gas equation of state. And we know for the ideal gas equation of state, our PV is equal to our nRT. So we can make V the subject. We know our N because they give us the moles of nitrogen, and then for carbon dioxide, so we can find the total number of moles. We add them together. We have 6 plus 2, that will give us the 8 kilomole. We know our R to be 8.314. Our T was given to us as 300 Kelvin, and then our P as 50 megapascal. So we'll change it to kilo pascal, right? And then we'll get our answer to be 1.3 meter cube. Now for real gases, we know that V real is equal to Z times V ideal. So for real gases, it's equal to the compressibility factor times the volume of the ideal gas. So before we get into that, we have to find our Z. We need our critical temperatures and pressure. So it's been given to us here. The critical temperature for nitrogen, critical pressure for nitrogen, critical temperature for carbon dioxide, and the critical pressure for carbon dioxide. Okay, and remember, for K's rule, we said we find an average of the critical temperature and pressure and use that to find our Z. So we call that the pseudo critical temperature and the pseudo critical pressure. So what we are going to do is that for K's rule, for our critical temperature, I'll multiply the mole fraction of nitrogen plus the critical temperature of nitrogen plus the mole fraction of carbon dioxide times the critical temperature of carbon dioxide. So I know the mole fractions, I can find the mole fraction. So for nitrogen, it need to be 2 over the total, that's 2 over 8. That's what gives the 0.25. And then for carbon dioxide, it will be 6 over 8. That's what gives the 0.75. Multiply them by the critical temperatures, then we get this value. Then we do the same thing for the pressure. So the mole fraction of the species times the critical pressure of that species. So when we do that, we will be getting this answer. So now we have our critical temperature and pressure. We can find our reduced temperature and pressure. So we know the reduced is just the pressure of the system divided by the critical pressure, right? So it's 15 over the 6.39. Always make sure the units are the same. So if this is in megapascal, then what you're working with should also be in megapascal. If this was a different unit, you have to change it to megapascal. Then we find the TR as well. So the temperature of the system over the critical temperature. Once again, unit consistency. So this is in Kelvin. And what was given to us in the question was also in Kelvin. So we are fine. Then we can come to the compressibility chart. So we have a PR of 2.3 and then a TR of 1.2. So let's come to the compressibility chart. Sorry. Okay, this is it. Let me just clean this up. I was doing some calculations earlier. So we know the PR to be 2.3 and TR to be 1.2. So I'll locate 2.3 for the critical pressure. So that should be, let me try and zoom in just a bit. So this is 2. If I check it, every 2 box will be 0.1. So this will be 2.1, this will be 2.2, this should be 2.3. So I can just trace this up. Okay, and then the critical temperature was 1.2. Sorry, the reduced was 1.2. So that's this curve here. So where it meets that line, we can just project it onto the y-axis. That should give us a value of about 0.5, 1, 2, 3, 4, 5, about 0.55, right? Let me check it now. That's 1.2. Yeah, and then this is 2.3. Okay, they were getting 0.49. Let me see where the mistake could be coming from. Okay. Okay, sorry. So I just punched this in on the calculator and I was getting 1.155. So we'll work with 1.15 instead. So let me clean this one. It's 1.155, so that's about 1.16. So it's actually in between the 1.15, that's this curve here, and the 1.2. We're not supposed to use exactly 1.2. So 1.156 would be slightly above 1.15. That would be somewhere here. So that's why if they project it, they were getting an answer about 0.49. So we may be having maybe 0.48. So just make sure that you are reading carefully from your compressibility chart, right? And don't round it off too much, but this was 1.15. If you make it 1.2, you'll be getting a different answer. So that would be the z that we would be expecting. So we can multiply. Remember we said that v real is z times v ideal. So we can multiply the v ideal we found, the 1.3, by the new value of z, so you are getting 0.49, and this is what we should get. So the thing about the compressibility chart is that your answers may be slightly different. Over here we are having 0.49. You may read and get 0.5 or 0.48, but what you get shouldn't be too far off from the actual answer. So if the actual answer is 0.49 and you are getting 0.55, then you know that there's a problem somewhere. So just keep that in mind. Now for Amagat's law, so this was for K's rule. For K's rule, we found an average temperature and pressure, and critical temperature and pressure. So that gave us the pseudo critical temperature and the pseudo critical pressure. So we multiply the mole fraction of the species by the critical temperature and pressure of the species. Now for Amagat's law, we are rather going to do that for the Z, the compressibility factors we find. So it means that we'll find the critical, so we'll find the reduced temperature and pressure normally, read as Z from the compressibility chart, then we rather find an average of those Z values. So when I find the Z for N2, I'll multiply by the mole fraction of N2. And I'll find the Z for CO2 and multiply by the mole fraction of CO2 and add them together. So for N2, the pressure over the critical pressure, I'll be getting 4.4. The temperature over the critical temperature, I'll be getting 2.4. So if I read from the compressibility chart, this was the answer that was gotten. Then we can do the same thing for carbon dioxide. So the pressure of the system, right, over the critical pressure for carbon dioxide, then the temperature of the system over the critical temperature for carbon dioxide. So please, for these ones, take the pressure and temperature of the mixture of the system over the critical pressure and temperature of the particular species. Then use that to find the Z for each of the particular species. When you are done, you can multiply the Z by the mole fractions of the species. And then you will find the Z you are looking for. Dalton's law follows the same format. It's just that instead of us working with PR and TR, we're going to work with VR, with the reduced volume, right, and TR. So for the reduced volume, it's going to be the volume of the mixture over nRT PC. So NR, so the number of moles, the universal gas constant, the temperature over the critical temperature, over the critical pressure. Now the problem with this is the volume that we put in here for the expression, we got it from um the ideal gas value we calculated. So the first one we calculated for the ideal gas is 1.33. So that's what we are putting in. Oh, sorry. Okay, so that's what we are putting in here, the 1.33. But the thing is that this volume was what we got for the ideal gas case. We don't know if that is going to be the actual volume for the real case. So it means that when we go through the whole process and find our answer, right? So they had 0.89 for the first answer. We'll have to put that answer back in. So we'll put the 0.89 back in here and then here as well. So we'll repeat the process with the new volume until the volume we are getting is not changing anymore. So there's a little table here that Doc did. So he first found the first volume 0.89, he found the second volume 0.74, and then the next volume was 0.7. So let's say 0.74, 0.7, they are not too far off, so we can just end it there. If you want to be very, very particular, you can continue the number of iterations, but the concept is just the same, right? So you find your VR, which requires that you know your volume over the whole of this expression. You can get the expression for your VR, you can get the expression for your TR. You can read them from the compressibility chart and get your Z. So if this is a compressibility chart, one of the things to take note of is which lines are for VR and which lines are for TR. It's very, very easy to make this mistake. Realize that for TR, right, these ones are the solid lines, and then for VR, from this particular graph, and these are the ones that you guys would have printed out, the VR are the broken lines, so don't mix them up. So the question gave us a VR of 2.14, so we'll locate a VR of 2.14, so that should be somewhere here. So this is the broken line for VR being equal to 2, right? Then we had a TR of 0. No, sorry, a TR of 2.4. So 2.4, this is 2.5, the solid line here. So 2.4 should be somewhere around that. So if we should continue along its end somewhere around here. So if we trace it, that should be giving us a value close to 1. That's why they had 0.99, right? So that's how we just read VR and TR together. So just make sure that you're looking at the correct line. Usually the VR are the broken lines and TR are the solid lines. Okay, so these are the examples in the rest of the examples to try out in the slides. So I made a PowerPoint just for those ones. We'll go over them, and then that will be the end for this particular video. Okay, so you can start it now. So we are saying that air is a mixture of nitrogen, oxygen, and small amounts of other gases, and it can be approximated at 79% nitrogen, 21% oxygen on a mole basis. During a steady flow process, air is cooled from 220 to 160 Kelvin at a constant pressure of 10 megapascal. Determine the heat transfer during this process per kilomole of air using the ideal gas approximation, K's rule, and then Amagat's law. So the most common things you'll be asked to work with are ideal gas, K's rule, and Amagat's. Usually Dalton doesn't come in because of the iterations you would have to do. Okay, so we have our system here. We have air. We have the composition of air on a mole basis. We know that it's coming in at 220 and 10 megapascal, and it's coming out at 160 and the same 10 megapascal. So for us to get the temperature to drop, it means you have to be removing some amount of heat. And the question was how to determine that amount of heat transfer that would be occurring during the process. So we can use the energy balance for an open system. We know that our K plus our W is equal to our H1 minus H2 plus our change in Ke plus our change in Pe. Since there is no work done, this can go away. There is no change in kinetic and potential energy, or we can assume they are negligible. We can just say that our K is equal to H1 minus H2. If it's on a molar basis, then we can say that our K is equal to H1 minus H2 with these symbols. So we're already familiar with these symbols. The change in enthalpy for one component can be estimated with H1 minus H2 for the pure case, right? We however have a mixture, so we would have to work with this formula. So this is what we would have expected for if it was just one species, if it was just hydrogen or nitrogen or oxygen. But we have nitrogen and oxygen in our system, so we'll do this for nitrogen. So we still see the H1 minus H2 for nitrogen, right? For nitrogen, but we have to multiply by the mole fraction of nitrogen. Then we find the H1 minus H2 for oxygen and multiply by the mole fraction of oxygen. Then we can add all of them together because we are dealing with a mixture now. Okay, so the first part of the question says we should work with the ideal approximations. Normally, before finding our change in enthalpy, we need to check whether our gases are going to be real or they are going to be ideal. So the question has said we should start with the ideal case and then work with K and Amagat's law. But in the case that you were not told, you need to determine whether you are going to be under real conditions, whether you are going to be under ideal conditions. If you are working with ideal conditions, you can just read their values from the ideal gas tables or work with the ideal gas equations, right? But then if they are real, they will need to find their departure from ideal behavior. So that's where the enthalpy and entropy departure charts come in. So we can check whether they are real or ideal based on temperature and pressure. So for oxygen and nitrogen, their critical temperatures and pressures are here. Nitrogen is yellow, oxygen is green. So we can see the critical temperature and pressure for both of them. And we can compare it to what we have in the question. So you can see that these values are way below what was defined for our system. So it means our gases are going to most likely be ideal. It will be real, sorry. What we are saying is that the values we are having here, the critical values, the values beyond which um, it becomes, or the values beyond which, I mean, if these values are very high, so if we are beyond these values, we are going to be ideal. Sorry, I keep mixing ideal and real. If we are beyond these values, we are going to be under real conditions, right? And the temperature and pressure given to us in the system, we were given 220 Kelvin, 160 Kelvin, and 10 megapascal. So if we should check it, 10 megapascal is already higher than both critical pressures for nitrogen and oxygen. And then the 160 and 120 Kelvin are also very high compared to the ones we have here, or they are just about that same value. So we realize that since the values are slightly above what we have, then we are most likely going to be under a real condition, right? Remember, once you're above the critical point, the system is not going to be like an ideal one, right? So once you're above the critical point, you're not going to be ideal, you are going to be real. So that's in case the question again states use this law, use that law, and you have to still estimate it, right? Okay, but the question told us that um, we should start with the real gas approximation and then work our way towards K and Amagat. So we can work with a generalized departure charts to find the value. So that's if we had um if it was under real conditions, we'll work with the departure chart. So we'll find the value under the ideal condition, and then we'll add the departure from ideal behavior to it. Okay, so we know that this is the formula that we have. H1 minus H2 is equal to H1 ideal minus H2 ideal. Okay, sorry about that. So we know that our H1 minus H2 would be equal to this formula. So this is one of the formulas that we are giving. So it's H1 ideal minus H2 ideal. This is just for the ideal part. And then the departure becomes this part. So what we are saying is that if it is not going to be an ideal gas, it's going to be a real gas, then we can work with this formula. We can find that H1 minus that H2. That's for just the ideal part. Then we add the departure from ideal behavior. So we can get these values as ZH1 and as ZH2 from our enthalpy departure chart. Okay, but then back to our ideal gas approximations, we can find our desired enthalpies from the ideal gas tables and plug them into the formula. So this was the formula we're looking for. We're looking at the first case for just the ideal gas. So if it's just the ideal gas, it can be the same formula, but then the departure term is no longer in there. So it means that our H1 minus H2, what we have here, H1 minus H2, because we're looking at ideal gas for the first part of the question, we won't include the departure terms in there. So the H1 minus H2 is just going to be H1 ideal minus H2 ideal, and we can represent it with this formula at the end of the day, because you want to find for the mixture, so multiply by the mole fraction, right? So all that we are just trying to say is that if you had, and if you wanted to find your change in enthalpy, you can use this formula. If it was an ideal gas, you work with, if it was just an ideal gas, you work with just this part. If it was a real gas, you first find the ideal gas part, then you add the departure part to it. So there's also a similar expression for entropy, right? You include the departure parts to it. But the first part of the question said we should do it for an ideal gas. So we are just looking for H1 minus H2. We're not going to include the departure into it. Then we multiply by the mole fraction for N2. Then we'll do the same thing for oxygen and multiply by the mole fraction of oxygen. So our temperatures were 220 Kelvin and 160 Kelvin. So we can go to the ideal gas tables for nitrogen and for oxygen, right? And then we can read the values. So at 220 Kelvin, we can see the values here for enthalpy. But then there's no 160, so we'll have to interpolate between the 0 and the 220. So that's what I did on this slide here. So I read the value for oxygen, and for oxygen is here, nitrogen is here at 220 Kelvin, right? Then for 160 we can interpolate. So the value that we are looking for, that's at 160, minus the lower value, which is 0, over 6391, which is this one here, minus the lower value again, which is 0, should be equal to our temperature of interest, that's 160, minus the temperature that this 0 corresponds to, so that temperature is also 0, then over the temperature that the 6391 corresponds to, so that's the 220, then minus the temperature that the 0 corresponds to, so that's 0. So when we do that, we can find our H2 for N2. And we can do the same thing for oxygen as well. So we are just going to interpolate between 0 and 220 and get our answer. Okay, then we can just plug it in there. So the mole fraction times H1 minus H2, then same thing for oxygen, mole fraction of oxygen, H1 minus H2. So this gives us the value if it is an ideal gas. Now we want to consider kh rule. So with kh rule, we'll find a new critical temperature and pressure using this relation. Remember, for kh rule, we are going to find a pseudo critical temperature and a pseudo critical pressure. So we are finding an average of our temperature first. So mole fraction of N2 times the critical temperature of N2 plus the mole fraction of O2 times the critical temperature of O2. Then we do the same thing for pressure. Mole fraction of N2 times the critical pressure of N2 plus the mole fraction of O2 times the critical pressure of O2. For the pseudo critical temperature, if you put in all the values, this is what we'll have. And for the pseudo critical pressure, if you put in all the values, this is what we'll have. So sometimes you'll be given the critical temperatures and pressures. If not, you'd have to read it from the table. The table will be just like this one here. So this is table A1. Sorry. This is table A1. So I think it's the first table in the list of tables you have, the document of tables you have. So you can read the critical temperature and pressure values. So these are the values, the critical temperatures, pressures for different species. Okay. I think I've gone too far. So if we do that, we'll find our pseudo critical temperature and our pseudo critical pressure. Then we can now find the pseudo reduced temperatures and pressures. So the temperature of our mixture or of our system divided by the pseudo critical temperature we found, right? That'll give us the pseudo reduced temperature. Then we do the same thing for the temperature point. Remember, we have 220 Kelvin, we ended at 160. So we do for both temperatures because we want to see what happens as the process happens. So from 220 to 160. So we'll find it for both temperatures. If you had a case where you had two pressures, we find it for both pressures. But in that case, we have it for just one pressure. So we find it for just that one pressure. It's the same pressure at the inlet and then the outlet. So because we are considering the departure in terms of enthalpy, we'll read from the enthalpy departure chart. So this time we're not reading from the compressibility chart because that one was used for finding volume. And now if you want to work with enthalpy and entropy, then what we are rather going to do is that we are going to read from the enthalpy and entropy departure chart. So for this question, remember, we said that K was equal to H1 minus H2. So we are going to read from the enthalpy departure chart. So let me just open that one up and then we can read from our chart. So we have coming that should be down here. Okay, so enthalpy, please make sure that you're always reading from the correct chart because enthalpy and entropy, if you mix them up, you make a mistake, right? So this is for our enthalpy departure chart. So let me clean what is here and then we can look at the reading. So if we are reading it, we have our first temperature TR1 to be 1.664 and then it's going with a PR of 2.67. So the PR is the same for the inlet and the outlet. So 2.67 should be somewhere around here. And then 1.664 should be somewhere around, this is 1.6, this is 1.7, so it should be somewhere, let's say, in the middle. So in between these two, I should be getting the value around here. Yeah, so if I trace it, it's very close to 1. So my ZH1 is the value at TR1 and PR. That would be a value close to 1. And I can do the same thing for ZH2. So that will be at TR2. That's the outlet temperature. And PR, the same PR because it's not changing. So TR2 was 1.21. So 1.2 is this is 1.2 here. So 1.1 would be very, very close. So let me just work with 1.2. And then if I should trace it, I'll be getting a value of about 2.5. So that's what we can see here. Okay, we can come back to our slide. Okay, so now this is the formula that we will need, right? At H1 ideal minus at H2 ideal. So you can now find the ideal enthalpy of the mixture points 1 and 2. And we've already done that from the previous part. So at point 1, that's at 200 Kelvin and 10 megapascal, and point 2, 160 Kelvin and 10 megapascal. We can get the enthalpies of oxygen and nitrogen. But we've done that previously, so we can just recall those values. But before we get into that, remember this was the formula we used, right, to find the K previously. But what we can do is, if we should do rearrangement, so if we should expand yn2 times h1 for n2 becomes the first one here. Then this yn2 multiplying negative h2 for n2 becomes this one here. Then yo2 multiplying h1 for o2 becomes this one here. And then this same yo2 multiplying negative h2 for o2 becomes this one here. You can rearrange everything so the ones at point 1 and at point 2. So we have h1 for n2, h1 for o2, h2 for n2, h2 for o2. So you group the like terms. You can bring a negative out here, factorize it out, and have this expression. So just something I wanted to show. So sometimes instead of working with this, we can work with this instead. So instead of working with the differences, so maybe H1 is for nitrogen at the inlet, H2 is for nitrogen at the outlet. Instead of finding that difference and multiplying by its mole fraction, we can find the value for the mixture at each point. So maybe at point 1, I'll find for nitrogen and oxygen, multiply by their mole fractions and add them. Then minus, I do the same thing for point 2. Right, so I'm saying this because sometimes you might see the formulas in different ways, but all in all, it's the same thing, right? So if you want to avoid all the confusion, you can just keep what we looked at previously, or keep this in mind, but know that it is also equal to this final form. It's just rearrangement and change of subjects. But we already have that part of the expression down, so we already have the ideal parts down, the H1 ideal minus H2 ideal. That's what we found previously, right? So we had 1743.7455 for that one. Then we know our RU, we know our TCR, our critical temperature. We know our ZH1, which we found, and our ZH2. We put all of that in there. This is what we will get. Now the final thing is to use Amagat's rule. So remember, Amagat's rule differs from Kirchhoff's rule in that we find an average Z instead of an average TR and PR. So we are not going to look for an average TR and an average PR in this case. We are rather going to find Z normally, right? And when we find it, we would now find an average of that Z. So we'll start with nitrogen. We have the critical temperature and pressure. So the reduced temperature of nitrogen at point 1 will be the temperature of the system at point 1 divided by the critical temperature of nitrogen, right? Not the average critical temperature, the critical temperature of just nitrogen. So that's what we have here. We'll do the same thing for the critical temperature of, for the temperature of nitrogen at the outlet. So at the outlet, it will be 160 for the system divided by the critical temperature of just nitrogen. So that's what we have here. Then for the pressure of the system divided by the critical pressure for just nitrogen. So that's what we have here. Then we can now read the value. So at TR1, so that's at this temperature, and then at this pressure, that's for point 1, the inlet. Then for the outlet, at this temperature, and then at the same pressure, because it's the same pressure as the outlet. So if you're doing it at point 1, this is the value we should be getting for our ZH1 for enthalpy departure. Then at point 2, we should be getting a value close to this for enthalpy departure. Then we can do the same thing for oxygen. So critical temperature and pressure for oxygen, we have at point 1. So the temperature at point 1 was 220 divided by the critical temperature for just oxygen. Then at point 2, the temperature at point 2 was 160 divided by the critical temperature for just oxygen. Then we go to the pressure. So the pressure at points 1 and 2 is 10. So we just need to find one of them. We just need to do it once. divided by the critical pressure for just oxygen. Then we can find TR1 for oxygen. TR1 for oxygen and PR for oxygen. We can find AZH1 for oxygen. So from the enthalpy departure chart, we can do the same thing at point 2. So now we have that, we can find the average of ZH at both points. So we have the ZH values. So at point 1 for nitrogen we had this. At point 2, that's the outlet for nitrogen, we had this. As the inlet for oxygen we had this, and at the outlet for oxygen we had this. So you can read from the chart so you can get familiar with it and you can compare your values. So if you want to find the average, it will be the mole fraction of nitrogen times the ZH for nitrogen at point 1. Right now we are looking at point 1, ZH at point 1. Right, so the mole fraction of nitrogen times the ZH for nitrogen at point 1, that's the 0.8 here, plus the mole fraction of oxygen times the ZH for oxygen at point 1, so that's 1.2. So we can get a value of 0.884. Then at point 2, mole fraction of nitrogen times the ZH of nitrogen at point 2. So this is point 2. Point 2 value, that's the outlet, plus the mole fraction of oxygen times the ZH value of oxygen at point 2. So that's this value over here. So we can put it back into our formula, our HID minus our H1ID minus our H2ID, which we've already found. And then we know our RU, our TC, our new ZH1 and our new ZH2. So these are the values we would get. Okay. So in order not to make the video too long, I'll take question 2 and 3 in a separate video. So to just be questions. So this one is just more like an introduction to all these shoes, K shoe, Amagat shoe, and all these things, right? And then for 2 and 3, I'll take my time and then do a separate video on those ones as well. So thank you for your time.